here we go. Okay, so this is going to be the last lesson we do for chapter 10. And I wanted to, I chose this because this was something I used to have students do a project on. It was one of the options this year, but nobody selected it. So I thought I would kind of cover it myself for you guys. So I want to talk about planar graphs. The history of planar graphs starts, well, the idea of a planar graph can be kind of nicely introduced with this thing called the utilities problem. So the idea is for houses on the street, you've got utilities that you want to bring to them. You've got gas, you've got water, and you've got electric, right? And so you've got a gas pipe coming in, you've got a water pipe coming in, and you have an electric cable coming into the house. And these things are generally all buried under the ground, right? Go out in front of your house, somewhere under the ground there, you've got pipes and cables. And so if you have these three utilities and you want to bring them into a home, no problem, 1, 2, 3, right? But when you have a bunch of houses lined up on a street and you want to start bringing those utilities in to each house, well, the question is it possible to do this without all of these crossings? Because every time you have a crossing, so looking in here, we have all these points where things cross over each other in this diagram, right? Every time you have crossings like that, you have like issues where pipes, you have to like, if you were gonna bury a pipe or do some maintenance on a pipe, you'd have to be careful not to hit the crossing pipe, right? So like if you're gonna do something with your water pipe, if you're gonna replace the water main, then you've got to make sure that when you're digging, you don't accidentally like hit the gas pipe, right? You don't want to hit the gas line while you're digging up the water main, right? So the optimal situation would be to have no crossings, right? Well, we can rearrange this to some extent, just pretending that we have nothing else going on around us. If we get rid of this one, we could make it go over here, right? Let's make it red. Make that go over there, and this one over here. Oops. This one over here, we could get rid of that and make it go around like that, right? But then you still have these other crossings here. And we still have various other crossing points here, here, and here. And I won't dilly-dally with this too much. You can try it yourself. You will discover it's possible to make all 9 of these connections without some crossing edges. So this idea is related to the concept of a planar graph. The definition of a planar graph is one where you have there exists a representation where no edges cross each other. Okay, now not every representation has to satisfy that rule, but there must exist some way to draw the graph so that no edges cross. So here's an example. If you look at the complete graph on 4 vertices, it is planar. Now, drawing the K4 graph, it's just it's got 4 vertices with all possible connections between them. And usually we draw K4 looking like that. That's kind of a common way to draw K4. But you could redraw that graph so that, say, the one edge that would go here, you can redraw it so that it goes around here instead. There we go. Got it. So that is a planar representation. It's a graph. It's the same graph. It's just that it doesn't have any crossing edges, right? However, an example of a graph which is not. Oh, hey, let's do one more. There's one more. Let's do one more example. Q3 is planar. Q3 is a 3-dimensional version of like a cube. So it's a cube because cubes are 3-dimensional. You can talk about like a hypercube, which is, like 4 or 5 or 6-dimensional. You can generalize this notion of a cube, and then those graphs that form cubes are called Q graphs, and so the Q3 would be the 3-dimensional version. So Q3, you can think of it, looking like this with two squares and then these connections between them. That is planar because you can rearrange it. And this nice way to rearrange it is to kind of make it like this, like two squares, one inside the other. And then take these edges here, they would become just lines that go like that. And so that's a nice rearrangement of the cube. It's kind of like you're looking at the cube with perspective from behind, and you're sort of looking through it like a hallway instead of seeing it from an angle like we were before. So you can imagine rearranging that thing in space, and perspective kind of puts it into a planar configuration. So instead of having all of these intersection points like this one and this one, actually, I guess there's just two. Instead of having those, you have none. So an example of one that is not planar is this one. This is K33, which is like a complete bipartite graph. We introduced bipartite graphs in a previous lesson, and this is a bipartite graph with three things in the first set and three things in the second set, and then all the connections you could possibly have, but only between the two two sets in the partition. So that is not planar. And to see why, there's this nice little sort of argument you can make that deals with like regions. So let's say you start with K22, and then we're going to start with K22, and we're going to like build up K33 from K22. So you have a bipartition with two sets. Let's make them like that. So here's the reds and the blues, right? And you make the blues, each blue is connected to all the reds, and each red is connected to all the blues. So a K22 graph is basically just this square, right? And then what you want to do is you want to add a vertex and then connect it to everything that you want to. You add a vertex, assign it to one of the two groups, and connect it to everything. But when you do that, you've got to choose where to put the vertex in your representation. And basically, if you look at this graph, the way this graph is drawn here, it divides all of two-dimensional space into two regions: region 1 on the outside and region 2 on the inside. And when you add a when you add a vertex to this graph, you're going to take one of those two regions and divide it in half. I'll show you. So take the same graph we had before, those two and those two, and then we're going to add one more vertex. Let's say I put it in the middle. Okay, if I put that one vertex in the middle, then besides these edges around the outside, I would also need to connect this blue to the reds, like so. Because I'm trying to make this a bipartite graph, I introduced another vertex to the blue team. And so that vertex needs to be connected only to everything on the red team. But now I have my region 1 on the outside, but now region 2 is split into two parts: region 2-1 and region 2-2. And this is basically without loss of generality. We could have placed the new vertex on the outside of the graph, and then region 1 would have been split into two parts in a similar way. So it's symmetrical without loss of generality. You put the new vertex in region 2 and it splits it in half. But now the question is, where do you put the next vertex? It has to be on the red team, right? Because we want to make K33. So it has to be red. Problem is, if you put it somewhere in region 1, then while it will be able to connect to that vertex and that vertex, it will not be able to connect to the vertex which is inside region 2. So if you put the new vertex in region 1, you get a contradiction. If you put the new vertex in region 2-1 here, then you can connect to this edge and this node and this node, but you can't connect to that node because of a crossing. And so that's a contradiction. And similarly, if you put the new vertex in region 2-2, you can connect to these two nodes, but you can't connect to that one without crossing. Contradiction. So in other words, and I say contradiction kind of because we're attempting to make this planar, and every time, no matter which of the three regions we place our last vertex in, we will contradict the assumption that this is planar, therefore proving that it is not planar. So, so I'll just leave one version of that argument on the page here for the notes. And this is impossible to make planar. So it turns out the question of whether or not a graph is planar has a nice theorem that sums it up called Kurotowski's theorem. But before I get to that, I want to talk about an application of this topic, why we especially for those of you studying computer science, why you might care about this. And the application comes up in circuitry. In the design of circuits, you have circuit components, which are like OR gates and AND gates, and various other things, whether they're like in actual electric circuits, you have things like capacitors and resistors and all sorts of things like that, right? Those are the circuit components. Those can be represented as nodes in a graph. So let's say you've got something like this, and then it goes like that, and then you have this, and then you have that, right? So this sort of thing can be sort of summed up as you have a node here, you have a node here, you have a node here, and then we have something that basically does this. Here's this X, Y, and P, Q, and R, and then you have sort of this scenario going on, and then you have this scenario, and then you have this scenario, right? So you can take a circuit and just take every component, make it a node, and then the wires connecting those components are the edges. Now, the question of whether or not the resulting graph is planar is an interesting and important question to computer hardware designers, because if you're going to have two wires carrying electric signals crossing each other, it's more expensive to design the circuit. When two wires cross each other, you have to do something to prevent charge from hopping from one wire to the other. If you had charge that hopped from one wire to the other, if they get too close to each other, they can you can literally be exchanging bit signals by exchanging electric charge between these wires. And I don't know all the physics, but they don't even have to be touching each other, because with magnetic fields, as long as they're close enough, it can hop over. So what you basically need to do is have them insulated. You need to have insulation in these wires to prevent that exchange of charge. And the insulation is costly. And it also makes the circuit more bulky and so on and so on. And so from a computer hardware perspective, you want to basically minimize the number of different crossings in the graph of your circuit. And so there's various techniques for this where often you can't avoid crossings. You have to have some crossings in order to complete the circuit. If it's possible to make the circuit with no crossings, then that's great. But if you do have to have crossings, then what they like to do is take the graph, rearrange it into subgraphs that are planar, as many large subgraphs that are planar as possible, and then just sort of use that strategy to kind of minimize the number of crossing points that you have. And so this study of planar graphs takes you into, you can define something called the crossing number of a graph, which is the minimum number of crossings required in a 2D representation, and then minimizing that, and finding a graph with a small crossing number, or finding the crossing number period of a graph is a problem that computer scientists are interested in solving. It's generally not an easy thing to do, because if you have a big, complicated, messy graph, it's really hard to do by hand, because it's really hard to rearrange it by hand and be confident that you've reduced the crossings to a minimum. Super hard to do. But there are algorithms that can solve that problem. So that is an example of why we care about planar graphs. So the end of this section introduces like a theorem called Kurotowski's theorem. Kurotowski. I don't no idea. I don't know where Kurotowski is from. So I don't really know how I should be pronouncing it, but it says, and I'll just go ahead and copy it over here. It's theorem 2 in your book. Polish. Thank you, Michael. Kurotowski is Polish. A graph is non-planar, meaning it cannot be drawn without crossings. It's non-planar if and only if it contains a subgraph, which is homeomorphic, there's a new word, homeomorphic to K33 or K5. So basically, K33 is that one we were examining. K33 is exactly this graph from the utilities problem diagram there. It's this graph that we were examining here. There's a little proof that it's not, like a little proof by contradiction that it's not planar. So that's K33. And then K5 is, of course, the demon summoning circle, as I fondly refer to it. That's K5. So did I get that right? Yeah, that's K5. Yeah. So if your graph contains something not exactly like one of these two, but similar to one of these two, then it's non-planar. And vice versa, if it's non-planar, it must contain a subgraph which is similar to one of these two. So I want to use this opportunity to talk about what a homeomorphism is. We had isomorphism. We talked about isomorphism previously. Iso means equal or same, and morphic means, morph means shape. But homeomorphism or homeomorphic, homeo means similar, which is not the same as equal, so similar shape. So the idea of a homeomorphism is it's sort of like an isomorphism, except it also incorporates, it's a looser function because it allows you to do to sort of reduce or increase the number of vertices by introducing a new vertex partway along an edge. So you can take an edge that's like this, and you can stick a new vertex in the middle. And so then you have one edge, which becomes two edges with a vertex. Or you can do a reduction where you have this situation and then you say, this is basically the same shape as a single edge, so reduce that down to just a single edge. And you remove a vertex and replace the pathway by a single edge instead. And that sort of idea of going back and forth between shapes like that is incorporated into the idea of homeomorphics. So as an example, you can look at a little sort of three-pronged octopus shape. Here's a node with three other nodes sticking out, right? It's like a little, this is called a star graph. So this is a star 3. It's a central node with 3 things sticking out. That is homeomorphic to a similar shaped graph that has 3 long legs sticking out. As long as those long legs don't have any branching, or as long as we don't have any branching like this, or any connections between those legs, then these two graphs are homeomorphic. They're basically the same shape. These 3 long legs can be sort of reduced down to single length pathways, and vice versa. Okay, so Kurotowski's theorem is about searching through a graph to check to see if it has any subgraph, which is maybe not identical to one of these two, K33 or K5, but it's at least the same shape according to this mathematical definition of a homeomorphism. Okay, that's it. So so that kind of sums up planar graphs. I want to extend this idea of planar graphs and show you an example of how this can then be applied to something else. And then this will sum up that'll finish up our lesson here. Planar graphs. So the idea of a planar graph can be related to maps. See if I can do this here. Yeah. So here's a map of the Midwest. All right. A map of a bunch of regions. As long as those regions are all contiguous. Sorry, Michigan. I'm gonna leave you out. I used to live in Michigan, so I'm rather fond of it, but it's not contiguous. So as long as the graphs are not contiguous or are like contiguous, then you can take a map and convert it into a graph. So what I'm going to do is I'm going to lower the opacity on that layer there. So that graph, I've lowered the opacity, and then I want to draw over the top of it. I want to draw on top of this map. I'm going to take each of the names of the states, and those are going to become nodes in a graph. And then what we want to do is connect the nodes if and only if those states share a border. So like Minnesota and Wisconsin will be connected, Iowa and Wisconsin will be connected, Illinois and Wisconsin will be connected like that. Of course, Wisconsin is my home state, so it is the center of my universe there. So, but Wisconsin is not going to be connected to Indiana because they don't share any border. Minnesota should be connected here and here as well to the Dakotas. Iowa will connect to South Dakota and Nebraska and Missouri and Illinois, as well as Wisconsin. Kansas will connect to Nebraska and Missouri only. Let's see, Missouri will be connected to Illinois, Illinois to Indiana, and Indiana to Ohio. So there we go. So, and we could have, in this case, we actually could have kept Michigan. In general, non-contiguous regions can mess it up and make it no longer planar. But in this case, it actually would have been fine. Sorry, Michigan. So the theorem is, well, one theorem you could say is that if you take a map and you form a graph out of it, necessarily the graph will be a planar graph. You think about that. Why does it have to be planar? It's because like this map already exists on a two-dimensional plane, and so you can't, and so like you can't really have borders between regions on a two-dimensional plane without it being something you can represent on a two-dimensional plane as a graph. Does that make sense? That's not a proof by any means, but it's true that this is always going to be planar. And then we have this thing called the four-color theorem. And the four-color theorem is a really famous theorem. It basically says if you have a graph like this, it's possible to make a coloring of it where you assign colors to the nodes in such a way that no two adjacent nodes are given the same color. It's the same thing like that you do on maps. When you color regions on a map, you make sure that adjacent regions are not given the same color so that you can tell the difference between them. And the four-color theorem says that for a planar graph, it is always possible to do a coloring with 4 colors or less. So looking at this map that I copied from the internet, there's actually more than 4 colors used. Let's see, you've got purple, red, yellow, green, dark blue, and light blue, and brown and gray. In fact, almost every state is given a different color, with some exceptions like Indiana and South Dakota, Wisconsin and Kansas, right? But they used 8 colors for this map. That's more colors than they needed to use. It is possible to do a coloring that satisfies the rule that no 2 adjacent regions have the same color. It's possible to do that with only 4 colors or fewer. In this case, I think you might be able to do it with 3. I think you might even be able to do this map with 3. But this theorem is really, really famous because it was really, really hard to prove. People thought this was true for a long, long time. And people were working on a proof of this theorem for years and years, and no one was really able to prove it until somebody decided to use a computer. And somebody programmed a computer to like check a vast number of cases. They were able to basically reduce the problem into a number of cases, but the number of cases was huge, too many to like check by hand exhaustively. So they programmed a computer to check all those cases. If the computer did it and proved that this theorem was true. But that proof by computer algorithm was like not really trusted originally. It was kind of contentious at the beginning. But eventually people were convinced. A lot of people spent a ton of time checking the computer's work by hand just to make sure the computer hadn't made a mistake. But eventually they were convinced and decided to trust computers. And since then, proof by computer, like computer aided proof as it is called, has become more and more common in mathematics and more accepted by the mathematical community as a valid way of doing things. So this was a sort of an important thing in theorem in math history because it ushered in the era of computer aided proof, which has expanded our capabilities pretty significantly. So that's it. I'll stop recording and we'll wrap up for the day. Thanks, everyone.